Today we're going to look at what random variables are. We're going to look at a discrete distribution, a predefined one, and then we're going to look at binomial distribution and Poisson distribution. And the important principles, I'll just go over them again, is that the concept of probability allows the uncertainty inherent in most decision-making to be modelled. What that's saying is that in all decisions there is uncertainty, or pretty much all of them. If there wasn't, it would be much easier to make the decisions. Even if we know what the outcomes might be of the decisions, we don't know how we might necessarily feel about the outcomes, and so on. And the second one is that theoretical probability distributions approximate the behaviour of real-life phenomena. And so using these distributions is how we can then, in a mathematical model, put in uncertainty and see, okay, what's the worst thing that could happen, what's the best thing that could happen, what's the thing that might happen on average, how likely are we for a certain thing to be within a certain range, and so on. And so what these probability distributions do is that they provide an approximation of real life. Now, we don't know what actually is going to happen, but we can at least get some idea about it. And that's the point of it all. Okay, so if we have a look at random variables, I'll start off here. So say we're interested in a value for the number of people in a queue at a supermarket. So say we're making up a model, a mathematical, Excel model even, where we're trying to simulate the queues in a supermarket, and we want to know how many checkout operators we should have on in order to be able to provide better service without wasting too much money. So we need to be able to represent the number of people in a queue. Now, the number of people in the queue, as you know, changes all the time, and it's not deterministic, it's probabilistic. It's according to probability. And so we want to be able to find out how can we model that so that we know approximately what range of values it will take and how likely it is to have each of those values. Another one is we might want to model the length of time a plane is overdue. So if we're trying to work out our timetables, we need to know the time it takes to get from one place to another is not deterministic, it's not certain. So we need to know what's the probability of taking a longer amount of time and what's the probability of different lengths of overdueness. Idea of how many tickets we'll sell for a concert. Any promoters want to be able to do that. Or if you've ever organised anything yourself and you're trying to set up for a party or a dance or whatever, is you want to have an idea of how many people are likely to come. And then in terms of the factory model or the production sort of stuff that you'll be looking at is the weights for bags of potato crisps. So if you've ever, those little bags you get in the big bag, sometimes you get about 3 crisps in them, and other times you'll get like about 20 because they have a highly probabilistic distribution because chips, they're either big or they're little and they get sort of stuck together in the hopper. And that's why those little bags are not allowed to be sold individually, because they cannot be precise enough in terms of their weights to make sure that each of those little bags has the right weight of crisps in them. They can be sure overall with the big packet of 12 little packets, but they can't be sure enough with the little ones. Okay, so all of these can be defined as random variables. So a random variable is a variable like X or Y or P or whatever, but it's random because it doesn't have a particular value. It has a range of values and it has probabilities associated to each of those values. So we don't know what the exact value will be, but we'd like to have a model of what values they can take and how likely each value is. So when the possible outcomes of a random situation are numbers, this is called a random variable. Now in the quiz you've got one question that's about identifying whether something is a continuous random variable, a discrete random variable, or not a random variable. Okay, now say I have a pile of job applications on my desk and I take one out and it will either be good or bad, say. Okay, now say I take one out and it's good or bad. Is that a random variable? Okay, well the answer is no, because there is no number associated with that. It was simply a yes or no. Okay, now say I have a pile of job applications on my desk and I take out 5 and I want to know how many of them will be good, will be acceptable, that I could appoint. That is a random variable because it will be a number between 0 and 5. So a random variable must be a number. So the first thing you think about, if something is a random variable, you have to decide, is it a number or not a number? Another example would be forecasting the weather for tomorrow. If we're talking about temperature, that's a random variable. If we talk about rain or no rain, that's not a random variable, it's an outcome or something else. Now, then we get to, so you've got the idea of random variable or not random variable, but as well as that, there's the idea of discrete or continuous. Now, discrete means that you can count it. It's chunky. So like the number of good job applications is a discrete random variable because it can be 0, 1, 2, 3, 4 or 5. It cannot be 2.5 or 1.3 or something like that. It only takes certain values. But continuous ones might be things like height. Height is a continuous random variable because you can take a person can be any height between a certain range, but they can be like 1.781, 1.782, 1.783, or you can even go more and more precise than that if you had the instruments to measure it. So that's what's known as a continuous random variable. So let's have a look at those four and just see if you can tell me which ones are discrete and which ones are continuous. Can anybody tell me which one would be discrete here? Okay, value for the number of people in the queue at a supermarket. Hands up if you think that's discrete. Hands up if you think it's continuous. Good, it's discrete. So we've got I'll just put a D here to show it's discrete. And that's because you can count them. You don't have 1.5 people waiting in a queue. Now, on average, you can have 1.5 people waiting in a queue. But we're not talking about averages here, we're talking about actual numbers. Okay, the length of time a plane is overdue. Hands up if you think it's discrete. Hands up if you think it's continuous. Yes, you're correct. It is continuous. Idea of how many tickets will sell for a concert. Discrete? Yep. This one actually is an interesting one because it's almost borderline. Because the numbers will be in hundreds or thousands or whatever, it's getting pretty close to continuous. So, in fact, you probably could model that as a continuous distribution, but really it is strictly speaking discrete. And there's often fuzziness in that because in terms of even this one here, weights of of potato crisps, are they discrete or continuous? Continuous? You're quite a lot today. So, yes, it's continuous. But in fact, in a way it's discrete because you can't measure beyond a certain precision. But basically, the ones that we're talking about are discrete, are really, really discrete, really chunky.